Just now we introduced the 4 quantum numbers of the electrons in atoms. So basically here now we know basically in one octet it can have 2 electrons. Okay. So now question: how many 2p octets are there in an atom? 2p octets. Think about it. 2p. So what's mean 2p? 2p means n. What's n number? 2. Yes. What's the L number? 2. 0. 0 means S. 0 means now it's P. 1. Yes. 1. So when now we know for 2p it means n equal to 2p. Okay. N equal to, right? P it means L equal 1. Okay. Now we need
3.
ML, right? Yeah. Now we get the. So we know if L equal 1, then ML can be minus 1, 0 or plus 1.
So there are 3.
Yes. So there are 3 octets. Good. Nice. Okay. So these 3 octets like this. Okay, 2p. So they have 3 orientations. So for 2p, it has 3 octets. Okay. Now, second question: how many electrons can be placed in the 3D subshell? How many electrons? And of course, basically 3D, right? 3D is mean n equal 3, L equal 2, right? And then what number of ml? How many ml? 5. Yes. So 5 is means 5 octets, right? So how many electrons can be in the 5 octets? 10. Yes. So how many? 10. So the way is like this. So n equals 3, right? L equal 2. And then the ml is 5 numbers. Okay, so it means it has 5 octets. 5 octets. Okay, so like this 5 octets. Okay, and they have different orientations. They have same shape because they are L is a C, right? But they have different orientations. So they have 5 octets. 5 octets. Yeah.
So what I'm saying is like C2P. When you see 2P, P is enough.
2p.
Is P is enough? Is P enough?
Yeah, P means L is equal 1.
And G means L is what?
There is equal 2. L is equal 2. Yeah, if L equals 0, yes, S. Now you know, right? Yeah, L equals 0, so it means the L means the shape, right? So if L is 0, so the shape is like a ball, right? So we call S orbital.
How many letters are there to represent L?
How many?
How many? Since like this, you know P, D.
Yeah.
How many letters like that?
Oh, you know, this is depends on how many elements we found, right? We found like now it's 119 something like this. So 119. So basically, D. That's all. No, enough, because we know if we build from 1s to like 5 or 7 f something like this. Oh no, and then D is 5. So the SPDF. Okay, so that's all. Because for these numbers, using these numbers, it can hold all electrons. now we found in on the Earth. Okay, and of course, in the future we can find more elements. Find more elements, and you know the periodic table, right? We can just fill the 190 something like this. Yeah, maybe you guys can. Maybe someone can find more new election like 120, 100. Yeah, this kind of oh, good.
He's so smart.
So 120 depends on you. Okay, good. Okay, so this now you know yes this is only 5F. That's all. Okay, and so now we know for 3D subshell it has 5 octets. So how many electrons? Yes. Yeah, it can be 10 and okay. So basically we can put the for each elements for each element. So we can put them into the table based on their electron numbers. Okay. So and then we know now for the rows are called periods, right? This means for example first periods, second, third, fourth. Okay. And then for all elements in one columns, we called groups. Okay. So this is like group 1, group 2, group 3. Okay. And also they have the similar like electron configurations. Now we introduce how to give their electron configurations. Okay. So basically, this is the octets in the atom. For example, 1 if n equal 1, so the octet is only 1s. Okay. When n equal 2, it can be 2s and 2p, right? And if 3, so it can be 3s pd. And if 4, it can be SPDF. So now we can say for each electron it has energy. And how to determine their energy? So we can use this equation. Okay, so this is called Rydberg equation. So this the energy of electron equal to minus the R, this is the constant, and time square of the 1 minus 1 divided by the square of n. So now n is the number, is n quantum number. Okay. So from here we can see the n number decides the energy of electron, right? Yes. And if the n number is small, what does this mean? If this is small, so this means this is large, right? Large. But here is minus. So this means it has low energy. It has low energy. Okay. When this number is high, is large, so this number will be small. So it minus small, so it means it has high energy. Okay. And this constant is the unit of this constant is joule. It's joule. Okay. So the energy unit is also joule. Okay. So So using this equation, we can determine the energy of the electrons. So if the atom only has one electron, like which element? Which element has only one electron?
Hydrogen.
Yes, hydrogen. For example, if it's hydrogen, so its energy. So all the octet's energy are decided by this equation. I describe this equation. Okay. But when there are more electrons in the atoms, So there are the energy, the Optus energy may change, okay? So this is called penetration effect. So this picture to show the energy level after the penetration effect. And if you want to understand why there are energy penetration effect, you should. Oh, okay. Another question is, you can get the book. Okay, you can get the book. You can read the book, and from the book you can find the answer why there are some penetration effect. Okay, and but here we can spend more time to explain what is the penetration effect. Which here we just only show you after the penetration effect, the energy level like this. And of course, you also maybe you can check, can find the answer from website. Okay, what is penetration effect? What is penetration effect? So here we don't have time to explain penetration effect. So after penetration effect, so we can say here and 1s and 2s is lower than 2p. Okay, 3s is lower than 3p, and 4s. Okay, and 4p is also lower than the 4d. 3p is low. The energy of 3p is lower than that of 3d.
The energy of 3D higher than 4S.
Yes, and also the 4s even is lower than 3d. Okay. Yeah, this is simple explain is that because the s orbital, the s orbital, can more close to the nucleus, so its energy, its energy decrease. Its energy decrease. Okay, because we know if the electron more close to the nucleus, it has low energy, right? And for the s orbitals, it can more easy to close to the nucleus than p and d. So in the same shell, the s has low energy than p, and also the p has low energy than d orbitals. Okay. Okay. Now we know the orbital energy like this. So after we get this, we can fill the electrons into the orbitals. So here we know this is about n equals 3, and this is n equals 3, L equals 2, right? Okay. For example, hydrogen. The first atom is hydrogen. Hydrogen has only one electron, and of course, it will put this electron in 1s orbital, right? So we can also write hydrogen like 1s1. So this is called electron configuration. So electron configuration is how the electrons are distributed among the various atomic orbitals in the atom. So here 1 is principal quantum number 1. Okay, and S is L. It means L. Okay, L here is 0. So 0. Also we write like S. So 1 it means number of electrons. Only one electron. So we write hydrogen like 1s1. It only has one electron. Okay. Okay. So hydrogen you can use this way. Second, helium. So it has 2 electrons, and of course one should be right here, right? So another should be also, because one orbital can have 2 electrons. Okay. but the difference is the spin direction. Their spin directions are different, right?
Yes.
So one is up, one is down. Okay. So the second one, okay, 1s minus 2. This means it has 2 electrons. This is 3 electrons, and of course, the third one should be put in the 2s, right? The 2s orbital has low energy than 2p. Okay? So like this. So it's like 1s2 and 2s1. Okay?
Yes.
The fourth one. So the fourth electron should be also put this side, right? This one, right? This orbital. So it can be. Yes. Okay. This. So where the fourth, the fifth electron should be?
1s2 and
2p1.
Yes. Yes. So like this. 1s2 2p, 2s2 2p1. Okay. Now 6. 2p2. Okay. So now the question is, this electron should be stay in this orbital together with this guy, or separate, or this. Which way?
separate.
Separate. Yeah, this is called Hund's rule. Hund's rule. So Hund's rule means the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. Right. So basically, so in this way, so what the total number of spins. So we know, for example, this is plus half, right? So plus half, add plus half. How many?
1.
How much? 1. Yeah, how much? 1. Yes. If so, should be like, so if it is together with here, so what the total number of the spin? 0. Yes. Because if this guy, if it's not here, so it must. So one should be plus half. Another must be minus half, right? So yeah, so we add it together is 0. And of course 1 is bigger than 0. So it should be this way. Okay? And the nitrogen. So the seventh, where? Should we stay together with them or separate?
Separate.
Yes, separate. Now what the whole what the total number of spin?
1.5.
Yes, 1.5. 1.5. Okay. So oxygen. So oxygen, the eighth electron must stay together because the energy of this orbital is lower than this one, right?
Yes.
So it must stay here. Okay. So it's 1s2, 2s2, 2p4, 2p4.
So,
Okay.
wait, can you go back?
Yeah.
So, is it S the mass one is 2?
Yeah, of course, because the first it has total A electrons. So the first electron should be stay in 1s, and feel this because this has low energy. It must at first it must be filled in the low energy orbital, and then so it must and so just the same and then just put like the S1 should be put here.
Okay, I understand.
Okay. Fluorine, and of course it should be here, right? So like this. The next one.
Right there.
Yeah, 10. Okay.
So, wait, Lasha. So, since these are kind of like different elements and everything, maybe because one is carbon and one is metal, like why the actually going different sides. Since like others are going in a positive direction, others are going in a negative direction. Is it because they're two different?
Yes, they must have two different quantum number.
Asking,
The MS should be different.
I'm asking, is it because there are two different elements? Like, okay, not elements per se, but yeah, elements by nature. Like one is
No, element also by the number of electrons. They have different electrons, so they have.
So it doesn't matter whether one is a metal and one is a gas. What only matters is the electrons.
The electrons are the same.
But
the atoms and the electrons in a single in an atom.
No, as in my question is it like the science and everything? Is it, since you remember like the part one I used to say versus gases or liquid or what?
oh, it depends on their whole physical chemistry. Now we just discuss the electrons, okay? And of course, we will introduce their properties. For example, for some elements, there are liquids, there are some are gases, some are solids. Yeah, just when this is depends on how the atoms stay together. Okay, yeah, depends on. And for example, if the interaction between the atoms is strong, so definitely they will be like metals. Okay, if is weak. Not, but for matter, for materials, for elements, also there are properties decided by they are molecular. Okay, they are molecular. So molecular, like oxygen, right? O2. Okay, yeah. But O2 is molecular, so the interaction between they are molecular. If the force between the molecules is strong, they will be like solid. If the phase is weak, so of course there's a gas. Yeah. This is one. Now we just only discuss like oxygen O2, right? This is molecular. Now we only discuss oxygen atom. Only one oxygen. Okay. Yeah. So, and of course there are molecular properties depend on the structure of their atom. Depend on their electron configuration of atom. Okay. Yeah, we will introduce more about their molecules later. Okay. So now, yeah. So here is the table to show you how to fill the electrons into the octets. Okay, like this in this column. Okay, you can just 1s, 2s, 3, 4, 5, 6, 7, and p 2, 3, 4, 5, 6. And so just using this way. So first 1s, 2s, and then 2p, 3s, 3p, 4s, 3p. Yeah, using this. Okay, this is a simple way. You don't have to remember the energy level. Okay, the picture of the energy level. But just this is a very simple way, right? Yeah. To figure out how to fill the electrons into the octets. Okay. Question. So what's the electron configuration of mechanism? So basically, you should know they are the atomic number, right? So what's the atomic number? 7? No.
8. Oh, what? 13.
No. So you should remember like the first 20 or 30 elements. Hydrogen.
It's been a while. It's been a while. It does another look at the
Go 12. Yes. So this is why you need to get a book. You can find all these contents out of the book. You know. So so now how many times do you want to borrow the book from college? I hope everyone. And also when you do like final test, so you also need a book. We're very helpful.
The open book?
No, the book. The last time I showed you the book.
Yeah, I mean the exam is open book.
Yes. Pardon?
The exam is open book.
Yes. Yeah, so of course.
Oh.
Yeah, so you need to get a book.
And I had the.
Yeah, because you know some students also they are not in here, so how to so that's the final test is not a book. So but the first thing is you need to get the book.
Yeah.
Why you open the book? What you open? You don't get it. You don't have a book. Where you open it? So basically before last time that day I talked to your monitor. You don't have it because my hand maybe 50 was okay. Yeah, 50 then maybe okay. Just give me and after the semester you give me back the book and return your money. Okay, and you do the keep the book clean. Okay, everyone keep the book clean. Also, before basically every student just borrow the books from the college, from our college. Okay. And so question: what is the electron configuration of magnesium? Yeah, 12. Okay, now we know the atomic number is 12. This means it has 12 electrons. Yeah. So how to write its electron configuration? Anyone want to try? Come and try. 2. So like 1s2, 2s2, 2p6, right? Anyone want to try? You want to try? Here.
So
you want to try? Yeah. You just follow like this, right? Follow this way. Okay, so 1, 2 is like this, right? And it's 2. So you can add here. Oh no, so happy. Oh, what's here? Join difficult. Yeah. Yes. Like first one is 1s, so it should be 1s2. Then 2s2. P. 2p, how many? P has 3 octets. 6, yes. So now you feel the 10 electrons, right? So another 2. Yes. Yeah. Okay, good. Yeah, thank you. You guys should also try yourself.
So those things we used to do back in high school where they would tell you the electric configuration, blah blah, is something like 2, 8, 2, like for example, your question was the electric configuration.
Yeah.
Yeah. So like that's used to go with the number of shells, the number of particles in the shell. Which was in the first shell, 2, then the second one she might have 8, then we can go back to 2 and then add up to 12. So like that is totally different from this.
I don't also mean.
So before, sir, like in high school, we were taught like this.
Yeah.
Like the way not this way, it was different.
How to high school how
Like
yeah.
this
Oh,
one
okay.
holds 2.
Okay. Yeah. I will introduce this.
Holds 8.
Yes. Okay. But the same, right? Okay, so one,
Then if for magnesium, it was supposed to be like this.
Yeah, that's
2, like
Yes.
so
2, 8.
equals 8.2.
okay, we will introduce this later.
Oh.
Okay.
So this is totally different from this.
Oh, no, it's the same. It's the same. First of all, this is like also 2, right? So the second is like A, right?
Yes.
This is share, subshare. So share is also A, right? Subshare, and then the third one is also 2. So 2A2, see? But this, of course, this is you more details, right? Yeah, and how this like A, where, what will the how the A electrons be, right?
It is,
Oh, it doesn't work.
I'm confused. Okay, so what did you did?
Me?
Yes, you. What am I talking?
Okay, yeah. So, yeah, the electrical current like this. So you see, so the subway, this is the first subway, 2. Second subway, it has A electrons. The third subway has 2 electrons. Okay? So we take it. Okay, the second question. What are the possible quantum numbers for the last electron in chloride? Quantum numbers. So this means just like you should think out where the last electron put in, right? Which orbital the last electron should be put in?
Is that fluorine?
Yeah, 17. Yeah, 17. Yeah, the total number of chloride is 17. So you just need, first thing is you should write its electrical configuration, right? And then you can figure out the possible quantum numbers. Oh, here, so last one, for this one, basically, we don't have to write all these out, right? So we can just use this, because this guy has this electric configuration. So we just like, so here's the same, right? Here's the same as this guy. So just using this way to show the electric configuration. Okay.
Confused.
Okay, so for basically the whole electric configuration is like this, right?
Yeah.
But we don't have to write all this, because here the inside, this part, is the same as this guy.
Yes.
So we just put just using this to represent this part.
What you're saying is we can use other elements to.
Oh no, but because first you know this is magnesium. Yeah.
Isn't that new?
No, no, of course, but the inside, this means the inside, but here is still 3s2. Besides the new configuration, it also has 3s2. Yeah. So we just use this simple way to write, to describe the electric configuration. Okay? Okay, now, so the question is about like, we also need to figure out the electric configuration of chloride. So chloride is 17. Okay, so it's like this, right? So you will say the last electron is put in the 3p orbitals. Okay, so what are the possible quantum numbers for the electron? Oh, yeah, that's okay. So in this orbital, what is the number? Yeah. 3. Okay. So N should be 3. What the so P? What the L number? 5.
1.
1. Yes. Because it's P.
Yeah.
P, the subshell is P. P is means L is equal 1. Okay. So ML can be can be yeah can be minus from -1 to 1. Yes. And MS number? Yes. Let's have a second one. So last elections added to 3p octet, right? So 3 octet and equals 3. The quantum number L must be 1. ML can be this, or this.
Yeah. So
Right.
3 orbits.
And also MS can be this. So this is the possible quantum numbers for the last one. So the last electron, ATM must be 3. L must be 1. But ML can be these 3 numbers. MS can be these 2 numbers. Okay? So any questions for this? Yes or no? Okay. So this table to show the configurations of the elements. Okay. So here we can see, for example, for this one, right? We don't have to write 1s here. Because 1s2 is purely. So you can just use it, and also like this. Okay. So this table to show the electron configurations of elements. And we can say for this, like 7s2, 5f4, and 6d1. So for this, it's more complicated than those. Okay, now we know in the periodic table, all elements in here we filled they are last electrons are filled in 1s, 2s, 3, 4, 5, 6s, right? So in this group, and for these elements, so there are last electrons are filled in 3d to 6d orbitals, okay? And for this, they're filled in p orbitals, and still another 2 is 4, 5, and f5. So this means for the same group, they are outside the electrons have similar field similar orbitals. Okay, so basically we call the electrons, the elements with s and p outside orbital electrons, we call them like representative elements. Okay, and this part we call them transition metal elements. Okay, and also this side is this period we call the lanthanide elements, and this is called actinide elements. Okay. And here to show the magnetic properties, we know for some atoms they will show magnetic properties. It's because this depends on the spin of the electrons. Okay. How should I bring it?